So this is a typical combustion analysis problem, which does tend to show up very frequently on the AP exam. In this situation, I have caproic acid, which is actually that smelly compound. You think of dirty socks, that's caproic acid. It's composed of three elements, carbon, hydrogen, and oxygen. And it has 0.225 grams to begin with. It's burned in the presence of oxygen to make CO2 and H2O, and I know the number of grams of each of those compounds that was produced. So we're going to try to figure out what the empirical formula of this compound is first, and then from that information we can use the molar mass to determine what its molecular formula is. Now this problem really forces us to take a step back and remember the law of conservation of mass. I have the number of grams of CO2. And if I'm able to find the number of grams of carbon that was contained in this sample of CO2, I should be able to make the assumption that all of those carbon atoms came from this compound. So therefore, however many grams of carbon are in this compound, that's the number of grams of carbon that came from this burned compound's caproic acid. The same assumption holds true for water. All of these atoms of hydrogen came from here. So if I can find the number of grams of hydrogen in this compound, I can assume that all those grams of hydrogen came from here. The tricky thing is the oxygen, because I have two sources of oxygen atoms in my reactant side. And these oxygen atoms could have come from the oxygen in the air or from the compound. The good thing is I only have three elements in this compound, so if I can find the number of grams of C and the number of grams of H, well, it should be pretty straightforward to find my number of grams of O. I'm going to give you about 5 minutes to work this out, and then from there we'll go over the solution with the empirical and the molecular formula. So the first thing that I did was I took my chemical equation that I constructed from the previous problem. I took my number of grams of CO2. I converted it into moles. And then that same assumption with number of moles of carbon, right? I have 1 mole of carbon for every 1 mole of CO2. I'm making that into a formal conversion factor here, and then moving back out into grams of carbon. I found the number of grams of carbon, and that should be everything that I need there. Now there's another way to do this. If you remember how to calculate mass percent, you can find the mass percent of carbon in CO2. So if I have 0.512 grams of CO2, I can find the mass percent of carbon, which was about 27%, convert that into a decimal and get the same answer. I think that's the quicker way of doing it, so that's the way that I'm going to do the hydrogen for the water. So I did the same thing. I took the mass of water that I started out with, I multiplied it by its mass percent of hydrogen to find the number of grams of hydrogen. So now I have two pieces out of the puzzle that I need. And from here, I know that I started with 0.225 grams of this compound. I found the number of grams of carbon that were in this compound. I found the number of grams of hydrogen that were also in this compound. If I take these two quantities away from my starting mass of the caproic acid, it leaves me with the mass of the oxygen that is left over. So now I have all three masses of these compounds, and of these elements, I should say, and this turns into a very straightforward empirical formula type problem. Starting with my grams of C, my grams of H, and my grams of O, convert those into moles, divide by the smallest quantity, and these numbers are rounding pretty neatly into whole numbers. I got a 3, a 6, and a 1, which means that my empirical formula is C3H6O. Now, in the previous slide, the molar mass was actually given to us. Molar mass was given to us as 116 grams per mole. Now that I've figured out my empirical formula, I need to find the molar mass of this lowest whole number ratio empirical formula to find out, okay, well, by what factor is that molecular formula bigger? If it comes out to be a ratio of 1, it's the same thing. If it's some ratio higher, I'm going to multiply those subscripts by that factor. The molar mass of this compound was 116 grams per mole, and if you calculate the molar mass of this compound, it comes out to be about twice the molar mass of this smaller ratio. So that means that this compound must have a molecular formula of C6H12O2.